Okay, we're on to page 3 of our latest attachment, and we get this kind of grand, important thing that we just, sort of loosely talked about without context before about how the integral provides rate or the net change in a function. So if you integrate the derivative of some function, you get the net change in that function from point A to point B. Um, so it's not just velocity that we can do this for. We can do this for any function ever in the history of the world, as long as it's measuring some sort of rate of change. So I give you this function r of t, which measures the rate of change of like water pumped in like gallons per hour. It talks about the flow rate. Or I think it's gallons per hour. But the function is modeled by 53 plus 7 sine of pi over 6t plus 3.6 plus 9 cosine pi over 12t plus 8.9. So part A asks you to find the maximum flow rate. So this is just kind of a tricky little thing, but this function actually already measures the flow rate. So it's not actually asking you to find an integral at all. Part A is just asking you if you want to find the max of anything, you want to take the derivative, you want to set it equal to 0, and you want to watch it go from positive to negative or negative to positive. So we're going to take the derivative of this thing. So r prime of t is going to be the derivative of 53 is nice, it's 0. We're going to keep our 7. The derivative of sine is just cosine of pi over 6t plus 3.6. Back inside for the derivative of pi over 6t plus 3.6, which is just times an extra pi over 6, because pi over 6 is just some number. And we're going to do the same thing with that cosine piece. It should be 9. The derivative of cosine is negative sine, so I'm just going to make this negative sine of pi over 12t plus 8.9. Back inside for an extra pi over 12. So if we simplify this thing a little bit, r prime of t is going to be 7 pi over 6. If we just merge these two numbers, and we just get a cosine of pi over 6t plus 3.6 minus 9 pi over 12, which you could just call 3 pi over 4, sine of pi over 12t plus 8.9. So boom, there's our derivative. And we kind of just want to set that thing equal to 0 and solve it. So let's do that. This is kind of a train wreck of algebra. So what you want to do is solve this using the calculator. I linked some videos on how to do that, and if you don't know how to do that, but you should be able to solve this in the calculator. You want to see when this thing is 0. So what I basically recommend is you type this into the graph feature of your calculator, and then after you graph it, your calculator can actually find the solutions for you if you just calculate the zeros, is how it basically works. Just depends on if you have an Inspire or an 83 or 84, how you kind of work your way through this. So the graph of this function kind of winds up looking like this. If we graph this r prime of t function, it's going to look sort of something like this. You probably want to change your viewing window so you only look between times 0 and 24, because this is measured in hours and hours of the day. So you can see that this function winds up being 0, 1, 2, 3, 4 times. So we want to find those 4 zeros, except we really don't have to. So if you do all the stuff in your calculator and you watch those videos on how to do that, or if you already know how to do it, it's kind of a tedious process in the calculator anyway. And you can find that these answers are 2.095. This one is 9.360. The next one is 14.181. And the last 0 is 18.861. The derivative, and it's maybe easier to see if you do these 1, 2, 3, 4 things, which are basically 2, 9, 14, and 18, 0, and 24. The derivative goes minus, plus, minus, plus, minus the whole time. So for you, that means decreasing, increasing, decreasing, increasing, decreasing. This is a min. I don't care about this one. This is a max. I kind of care about that one. This is a min. Don't really care about this one. This is a max. Kind of care about this one. but also don't forget to check your endpoints. So 0 was a potential max, and 24 was a potential min, which means we actually don't care about that one either. So we're pretty much good to go. We just need to plug in 0, 9.360, and 18.861, and whichever one gives us the biggest thing gives us the biggest thing. So we're pretty much good to go. So let's just do it. If you plug in 0, again, you're going to need your calculator. Also super important for this problem, since there's trig and stuff involved, you got to make sure you're in radian mode, otherwise you're going to get some weird answers. So just plug in 0 into the function. Again, this is a calculator process. Don't expect you to know what the sine of 3.6 is. But you want to plug these into the r function. We know these values already make the derivative of 0. So if you plug this into r, this guy's going to get you 42.113. You got to trust me on this one, or you can compute them yourself, I guess, if you really, really want. The next one's going to give you 61.713. And the next one's going to get you 61.117, which makes this the winner. So there's your max. And we'll just look at like the part B part of this, which is like not a ton of work. And then we're pretty much done with page 3, short and sweet. They kind of like to do this on the AP exam, which I guess you already kind of took, so they maybe didn't do this on your AP exam since you took a modified one. But they kind of like to give you the rate of change, aka the velocity of the function. That way you can kind of go forward and backwards, that you can take velocity and go forward to acceleration, or you can go backwards, take the antiderivative and go back to position. This is the same thing, it's just about gallons and stuff. So anyway, if we look at part B is the much, much, much more straightforward. How many gallons flowed through this thing in a day? So you want to just integrate from 0 to 24 the r of t function. So what kind of helps me think my way through this is like the r of t function looks like, who cares? It maybe looks like this. And you're finding the area under that curve from 0 to 24. So let's call that 24. Really, when you're integrating, you're finding like infinitely skinny little rectangles. And the height of that rectangle is r of t, which is in gallons per hour. And then you're multiplying it by the little base, which is what this microscopic little dt is, which is in hours. So this is gallons per hour, and this guy's in hours. And when you multiply gallons per hour with hours, you get back gallons. And essentially the integral symbol, we talked about this like weeks ago, but the integral symbol is basically a big giant sigma that adds up all those microscopic little rectangles. So it's adding up all the gallons of all these like tiny little microscopic subintervals to get you your total gallons. There's a way to do this integral in the calculator as well. I think I mentioned that in the last video, but you can actually just type this into the calculator and do this one. You can find the antiderivative here, but it's kind of going to be ugly. It's going to take a little while. These questions are sort of more conceptual about, do you know when to integrate versus do you know how to find an antiderivative and plug some stuff in. So just type this into your calculator. On the old school 84s, it's math and then the 9 button. But if you have one of the newer ones, it's a little more intricate to get there. Not that much. But you just need to type this into the calculator and just have the calculator do this for you, and you should get 1272. Again, watch those videos. It should tell you how to do it with the calculator. You can also probably just Google integral calculator, and you don't have to do it with an 83 or an 84 or an Inspire. You just have to tell the or your whatever website is running this thing, and just tell it what the function is, and it'll do it for you. Well, there's probably even an app. I should look for an app that does all this stuff for you. But that one's done. And we're going to look at one old AP question on the 4th page, and then we're basically done for the 6th week.